Since we have talked about natural exponential and natural logarithmic functions, we should also talk about bases other than t, which we'd usually call the general exponential and the general logarithmic function. In this slide, we're just showing again the definition of the general exponential and the general logarithmic function. In this specific case, in terms of the natural exponential and the natural logarithmic function. So, our differentiation rules for bases other than t would be the following. For it's almost the same in the chain rule version. A raised to u, where u is a differentiable function, a is not equal to 1, a raised to the derivative of a raised to u is ln a raised to u times u prime. So there. While logarithm to the base a of u, its derivative is u prime over ln a times u. So it's for this one, it's similar to u prime over u, you just add ln a. This one is the same as e raised to u. It's e raised to u prime, you just add ln a. So let's do that. Let's first do it for number 1, 2, 3, and 4. Yeah. So first for number 1, we have y is equal to 3 raised to 5x. Hence, we're going to find the derivative of this. Y prime would be equal to ln of 3, that's ln 3, times 3 raised to 5x. That's the derivative of 5x, which is 5. So just double checking the formula. That's ln a raised to u. So there. So if we are to simplify this, we're going to get y prime is equal to, that's 5 ln 3 times 3 raised to 5x. We can stop here, but we can still further simplify this by having y prime is equal to ln of 3 raised to 5 times 3 raised to 5x. Any one of this is already accepted as the answer. So doing it again in number 2, we have f of x is equal to 4 raised to 3x squared. Hence, f prime of x will be equal to ln of 4 times 4 raised to 3x squared times the derivative of 3x squared, which becomes 6x. So therefore, what we're going to have here is that f prime of x going to have 6x ln 4 times 4 raised to 3x squared. You may want to simplify that further as x ln of 4 raised to 6 times 4 raised to 3x squared. But any of the two is already accepted. So that's for general exponential functions. If we are to look at general logarithmic functions, for example, in number 3, let me start here on top. That will be y is equal to the logarithm to the base 3 of x. So y prime, according to our rule, would be the derivative of x is just 1 over ln 3 times x. So we can rewrite this as y prime is equal to 1 to x ln 3. So there. If we're going to have a bit more complicated than that, if we have number 4, we have number 4, f of x is equal to logarithm to the base 5 of square root of x squared minus 1. So following our same rule, f prime of x becomes the derivative of the one on top. Just a bit more complicated. So maybe let's first find the derivative of the one inside. We have u is equal to the square root of x squared minus 1. So therefore u prime will then be equal to, this is the same by the way as x squared minus 1 raised to 1 half. Hence u prime will become 1 half times x squared minus 1 raised to negative 1 half times 2x. This cancels out, so we get the u prime of x squared minus 1 raised to negative 1 half times x. So that's where we get a bit complicated there. And this actually becomes x over x squared minus 1 raised to 1 half percent of x. So applying now our rule, f prime of x now becomes u prime is x over square root of x squared all over ln of the base, which is 5, times u, which is keeping up with this one, that's just x squared minus 1 raised to 1 half. So with that, we'll simplify this as x over x squared minus 1 raised to 1 half times 1 over ln 5 times x squared minus 1 raised to 1 half. So this gets simplified into x squared minus 1. So I'm going to have x times 1, that's x over ln 5 times x squared minus 1. We can leave your answer like this, but you can also answer this as f prime of x is equal to x over x squared ln 5 minus ln. You can also answer it like this, but you can also answer this one already. So that would be the derivative of general exponential and general logarithmic functions. The other items are for your practice. Now, on occasions, it is convenient to use logarithms as aid in differentiating non-logarithmic functions. This process is called logarithmic differentiation. Because if you're going to look, for example, it's kind of difficult to differentiate this. Because our rule for general exponential is a raised to u. But this is a variable raised to a variable, which is kind of difficult to do. We don't have a specific rule for that. So we first are going to use the logarithmic rules, the one that were discussed before, for us to have a better way of finding the derivative of these functions. So let's do number 1. So in number 1, we have y is equal to x raised to x. For us to bring this down, we're going to have ln y is equal to ln of x raised to x. So we apply logarithm on both sides. So we cannot just apply logarithm on one side. We apply logarithm on both sides. With this, following now the rules of logarithms, this becomes x ln x. So there you go. So now with this, we can now apply implicit differentiation on the derivative of this. So the derivative of ln x is 1 over x, or u prime over u. So the derivative of ln y in terms of x will become y prime over y. We can write dy over dx over y as what we're used to, and you can also use y prime. So I'll just use dy over dx over y, although it's a bit more complicated. Now, from here, we can then apply the rules of our basic rules of differentiation here. So since this is product, so we would use product rule. So derivative of the first one, which is 1 times the second, ln x, plus the original first times the derivative of the second. So 1 x. This gets cancelled. Hence, we have dy over dx all over y is equal to ln x plus 1. And since we're solving for dy over dx, we need to cross multiply. Hence, dy over dx becomes y times the ln of x plus 1. But the value of y is x squared, is x raised to x rather, so we can replace it here. So dy over dx is equal to x raised to x times ln x plus 1. So finally, distributing this, therefore we're going to have dy over dx is equal to x raised to x ln x plus x raised to x. This is the derivative of x raised to x. So that process is what we call logarithmic differentiation. So let's try it on number 2. So on number 2, we have y is equal to 1 minus 3x raised to cosine x. So therefore, we first apply logarithm on both sides. You can use any base, but to make it simpler, let's just use ln. So ln y is equal to ln of 1 minus 3x raised to cosine x. Hence, ln y becomes equal to cosine x times ln of 1 minus 3x. So now we can apply our rules of differentiation. So from here, this becomes dy over dx all over y is equal to the derivative of the first, which is negative sine x. There you go, negative sine x times the original second one plus the first one, cosine x, times the derivative of ln of 1 minus 3x, which is negative 3 over 1 minus 3x. There you go. So simplifying this, we're going to get dy over dx all over y is equal to negative sine x ln of 1 minus 3x minus 3 cosine x all over 1 minus 3x. We can combine this into one expression, but we can leave it as is. It will get more complicated, since we need to also multiply y on the other side. Hence, we're going to have dy over dx is equal to y multiplied to negative sine x ln of 1 minus 3x minus 3 cosine x over 1 minus 3x. There you go. Since y is equal to this, we would have to distribute that y. So dy over dx is equal to, let's distribute. I'm going to distribute first the y before changing it to its original form. So that's negative y sine x ln of 1 minus x minus 3y cosine x over 1 minus x. This y here has this value. So that gets replaced. Therefore, the final derivative of 1 minus 3x raised to cosine x becomes negative 1 minus 3x raised to cosine x sine x ln of 1 minus 3x minus 3 times ln of 1 there's no n. 3 times 1 minus 3x raised to cosine x all over 1 minus 3x. If you would like to combine that into one fraction, go ahead, although it will become more complicated. So that's the process of logarithmic differentiation. So in this video, we'll look into the derivative of general exponential, general logarithmic functions, and the process of logarithmic differentiation.